Well, let's look at another shape property. This is moment of inertia. This is on page 650. Now this is area moment of inertia. There's two different ones. There's area and mass moment of inertia. We're doing area moment of inertia. And if you're taking physics, you might be using mass moment of inertia, which is related, but a little bit different. So why don't we look at page 640. I'm going to ask you some what are hopefully obvious questions, okay? First thing is that when you load a beam, you bend it, okay? Beams flex when they're loaded. And typically in engineering applications, we want to minimize this. We don't want things bending too much when we bear load with them. All right, so if you're going to build a floor, you put what are called joists underneath it. So which floor joist would have the least bending for a given load? One would hope so, yeah, the big one, right? So when you're designing stuff, make it big. That's always the idea there. Yeah, that's true. Now the material would matter, you're right. Okay, now those beams there are the same size, but how would you turn the beams to bear the load, top or bottom there? What's the best way to bear the load? Because the beams are the same size, and my point here is there's more than just area.
Beams are more rigid on their sides. So
yeah.
The top one's going to hold more load than the bottom one.
Because it's got a bigger dimension that way, right? Here you got the weak dimension going into the load.
Yeah.
There you got the strong dimension. So yeah, we'll go with that. Yeah. So there you go. So my point there is it's not just the size; it's how you orient it to. Okay, so a moment of inertia is a way of quantifying what we were just going over. Okay, the definition of a moment of inertia is that taking an object up and breaking it into small pieces, finding the area of each small piece, the distance from an axis to that area, and you square the distance. Multiply it by the area, and then you do that repetitively for an entire object. So you integrate to add everything up. That's what integrals do. They add stuff up. So to get Ix, you take the integral of y squared times dA. dA is the little area. Y is the distance from the axis to the area. The two factors that create a large moment of inertia are area and distance. So not only do you want a big area, you also want to get that area away from the axis you're calculating about. Okay. Now the units on moment of inertia are strange. They're length to the 4. So inches to the 4, meters to the 4, things like that. They're rather odd, but this idea is a little bit more abstract than centroid. I could point to an object, say the centroid is here, but with a moment of inertia, it's a little bit more abstract what we're talking about here. I think of a moment of inertia as being the cross-section of a beam's resistance to bending. That's how I think about it. All right, so there's a beam. Now down the length of the beam in the middle, down the centroidal axis, is something called the neutral axis. It runs down, if you take the centroid there and run it down the length of the beam, it's what you call the neutral axis. When you load up a beam, it'll bend. It's called flexing a little bit. And what you'll have is the beam has to hold itself together. It's got atomic bonds that link together and don't allow one atom to slide with respect to the other. So if that's the case, what you're going to have here is what the beam wants to do is what you're seeing on the right-hand side. Those sheets of atoms want to slide one across the other when the beam flexes. But what the beam's forced to do because of those atomic bonds is hold a right angle there, as you see on the left with the binding of the book. So what happens here is the beam has to go into this shape. This side has to get pushed in, and that side has to pull out. So you get compression on the top of the beam and tension on the bottom when a beam bends, okay? And the neutral axis, which runs down the centroidal axis, it has neither tension or compression. That's why it's called the neutral axis, okay? So that's what we're looking at with this moment of inertia, okay? So we want to make beams that have a high moment of inertia while using a small amount of material. Well, if you use a small amount of material, you lower the cost and the weight of the beam, which is what you want. So what types of shapes do we use for our structural elements? What does this? What has a low amount of material, but a high moment of inertia. What type? I-beams, right? Heard of I-beams? Okay. So let's look at what's happening with an I-beam. Maybe that wide flange beam is the place to look. See, here's the neutral axis through the centroid. What they're doing, they're putting those big flanges out away from the neutral axis. They're using their area as efficiently as they can. They're setting it out away from the neutral axis. If you look at columns sometimes, they make them out of tubes and pipes. They bend a little differently than beams. They kind of bow one direction or the other if they're loaded. So you want to get that material out away from that central axis about which they might bow. If you want to get more stiffness out of them too, you just fill them with grout. That gets them a good bit stiffer too. Good trick, okay? Now, if you look at the beams from 100 years ago or so, they were American Standard. That was the shape, like that. Okay, narrow flanges. So what we have on these beams is we have in the middle holding it together is the web, and then these things on the extreme ends are called flanges. Okay. So American Standard beams had kind of relatively small flanges that were rounded. Filleted is the term. What's that?
Why were they filleted?
Could have been for fabrication. I don't know. I'm not sure why they filleted those.
If you're going to weld two beams in the fillet, it's easier to weld a.
Could be.
Weld two filleted things.
Did they like extrude those?
Yeah, basically, yeah. And I'm not sure, there could be attached to them. I don't know. I don't know why they were built that way. But they've changed. They use wide flange beams now. And one thing that a wide flange has that an American Standard does not is a wide flange has strength if it's loaded laterally from the side. Okay. Normally, when we're putting beams in, we think about them being loaded vertically, down. But now we look a little bit at the side. Why do you suppose here in the Northwest we look at sideways loading? Yeah, earthquake. That could be big. Okay, wind and things like that, but earthquake especially. So we want strength laterally as well as vertically now. So wide flanges are the more normal type of beam. There's also miscellaneous beams, which are neither standard nor wide flange, and there's heavy pile, but that's used more for like bridge footings and things, where they just pound those into the ground with like a pile driver, which...
The American Standard are pretty much obsolete, right?
Yeah, for the most part. A lot smaller stuff you might use it, but yeah, they're not used as much anymore, just because they don't have that lateral strength. Okay, T-beams are half of a I. You cut them in half. Channels are half cut the other way, and tubes and pipes are used for columns. Okay, so there's some pictures of some structures. You see the I column and I beam there. Kind of hard to see it, but a little bit better view right there. There's a typical joist for a house now. They used to be 2-bys that you'd use. Not anymore. Now they use this TJI stuff, which is really just an I beam. You get that kind of cheap press board in there. You can save a lot of money with the weight and material on that. Okay, and you got like a laminated kind of plywood flanges on those things. There's some double T-beams, big massive concrete T-beams. There's a tube being used as a column. Okay. All right. So I-beams are called out in a certain way. They're called out by shape, by nominal depth, by weight per foot. So a typical call out is a W, which means wide flange, 36, which means the depth is about 36 inches. Not exactly maybe, but in the ballpark, so they can put them together into categories when they make a table of beams. And then it weighs 300 pounds per foot. The structural engineers want to know the weight per foot so they can do their design work based on that, okay? So shape, nominal depth, weight per foot. Okay. All right, so that's just a little bit of what's going on with that. They have tables for beams. You can look up different values for them. They're standard shapes. You can look up tables of I-beams on the internet, and you get all that information that you need to do design work with. Now let's have a look at how this work is done. So let's look at a rectangular cross section. So this is on page 660. So let's look at how we could find the moment of inertia of a rectangle about its own centroidal axis, which is often where you take moments of inertia about. So what we're going to do, we're going to use this integration formula, the integral of y squared dA. So we're going to take this, calculate this about an axis. When you're doing moments of inertia, you calculate about an axis. All right, we've got the base and the height. So we're going to calculate it about this centroid here. We're going to use this y squared dA formula. So when we start integrating, we'll start at negative h over 2. And when we finish, we'll stop at h over 2. Those will be our limits of integration. We got to break this thing up into little pieces. So we want a single distance from the axis to the piece. So that'll be the y part of the y squared dA formula. So we're going to measure up from the x-axis. So we want little pieces that are parallel to the x-axis, so they have one y distance. So we'll call that dy, okay? So we're going to measure up a distance y. We're going to square that and multiply it by the area of that little rectangle up there, which is what, b times dy? Our upper limit will be h over 2, and our lower limit will be negative h over 2. There you go. So we'll run this number and we will see what we get for a moment of inertia.
So y equals y?
Yeah, we're just gonna.
An easy one. What if there was like a complex shape that like equal?
Yeah, right. So we're keeping this one's a fairly simple one because it's a rectangle. Yeah, I think of these integrals as being like computer, like a program. You know, measure up a distance y, so that's just y. Figure out the area, square the distance, and multiply by the area. That's what we're doing. Okay. So we're going to integrate y squared dA, which is y squared b dy. We're going from negative h over 2 on the bottom to h over 2 on the top. Okay, I'll pull the b out because it's a constant. I'll be left with the integral of y squared dy, limits of negative h over 2 and positive h over 2. Integrate that y squared, I get y cubed over 3. The base is on the outside. I'll pull the 3 out too, so I'll get base over 3 times, and I'll plug in h over 2 cubed minus a negative h over 2 cubed. So I'll get b over 3 times h cubed over 8 minus a negative h cubed over 8. All right, so now we got to work with fractions here a little bit, if you remember doing all that. H cubed over 8 minus a negative h cubed over 8 is 2h cubed over 8. So that becomes h cubed over 4 times b over 3, which is bh cubed over 12. So that's the moment of inertia of a rectangle about its own centroidal axis. That's a very common formula. That's on your formula sheet on the right-hand side, I think. Upper right, maybe? Can't remember. Middle right. All right, now where they put the axis matters. So that's the axis through the centroid. If you put the axis on the bottom, you go through a similar integral, except the limits are different. So instead of going from negative h over 2 to h over 2, you're going from 0 up to h. Okay? So you're going to take the integral of y squared dA again, which is y squared b dy. But instead of going from negative h over 2 to positive h over 2, we're going to go from 0 to h. So we're going to the integral of it, y squared is y cubed over 3 times the base is by cubed over 3. Plug in the limits, you get bh cubed over 3. So where you take the moment of inertia about matters. Where the axis is matters. Okay, that's what we're figuring out here. So if I take the moment of inertia of this rectangle here about its own centroid, it's bh cubed over 12. But if I take a moment of inertia of a rectangle about its own base, it's bh cubed over 3. So it's 4 times as big. Okay? All right. Now that's the basics of the derivation there for a rectangle. And we could do a lot of calculus, but turns out people have done a lot of the calculus for us. So this is on your formula sheet. Yeah. So we got the moment of inertia of a rectangle is bh cubed over 12. That's through its own centroid. For a triangle, it's bh cubed over 36. For a full circle, it's pi r4 over 4. And for a quarter circle, it's 0.05488 r4. So those are the moments of inertia of common shapes.
In the x direction only?
Well, if it's symmetrical, all those would work in the line because they're all pretty much symmetrical. I'm on page 680. It's on your formula sheet. Okay. So those will, if you just rearrange those a little bit, if you just change the definition of base and height, that'll work for I sub y also. All those equations will, yeah.
So it's kind of off topic. Would you ever involve a double integral to find,
I've seen people do it, yeah.
like, not in like a 3D space, but really just
No, it can be done in 2D also. Very honestly and frankly, I don't do a whole lot of double integrals.
Okay. I just was curious if we ever will approach that.
I've seen people.
Do like a 3D shape.
That's what I thought.
No, actually, I've had people do them in 2D also, because I've done homework with calculus, and I've seen people throw double integrals at me, and I had to scratch my head and figure out what they were doing. So you can do it. It wasn't all that bad.
I like just disable it.
Yeah, I kind of do too. But yeah, I've had people do double integrals on homework before.
When you do double integrals, when they're like going like that or something, so then you need to do math.
I can't. It's been a while, so I can't quite remember when I saw it, but I've seen it before, and it wasn't that complex either. I just looked at it, kind of figured out what they were doing, so it was okay. All right. Now, those are moments of inertia about centroidal axes, but sometimes when you have composite shapes like what you see there, a T-beam, you may not be taking the moments of inertia about the centroids of each of the shapes, of each of those rectangles. If you have a neutral axis here, you often want to take the moment of inertia about it. You're going to have to find the moment of inertia of this top rectangle about that neutral axis. And then also find the moment of inertia of the lower rectangle about the neutral axis. So we have to have a way that we can take a moment of inertia about a place other than its centroid. And we don't want to be doing calculus all the time. We want to keep this a little more simple. So we use these tables and something called the transfer axis theorem to do that. Okay. So the transfer axis theorem is on page 690. So what that tells us is if we take the centroidal moment of inertia, the moment of inertia of an object about its own centroid, and then add the area times an offset distance squared, we'll come up with the moment of inertia about an axis other than a centroidal axis. So there's an example. I've got a shape up there. This is on page 682. And I can find the moment of inertia of that shape about its own centroidal axis, so I'll put that in red about this axis. Okay. But if I want to find the moment of inertia of that shape about this axis up here, I just use my red moment of inertia, I bar x, and then I add in a term called the transfer axis term, which is a times the distance 1 squared, 80 squared.
Is it only for symmetrical shape?
No, it'll work for anything. As long as the axes are parallel, you're good. Now, the moment of inertia then, let's just look at this. I bar x for this shape would be the integral of y squared dA. If I want to find the moment of inertia about an axis that's parallel but not through the centroid, that would be down here. All of my y's now have an extra term, an offset term of d, because I'm offsetting that axis d. So instead of y squared dA, I got y plus d quantity squared dA. Okay. Now, I can use the FOIL on that. I get y squared plus 2 times d times y. Now, that's not a dy. It's not a calculus dy. That is a d times a y. And then plus d squared dA. Okay, I can distribute the dA through. I'll get y squared dA, the integral here. That's just I bar x. Then I've got d squared times the integral of dA. Well, the integral of dA is just a, so that's ad squared. And that term in the middle, what it's going to do is cancel out, because I got a y dA. For every dA below the axis, I got a dA above the axis, because that's the centroidal axis. Those things will just balance out and zero out when I add them all up. So that middle term goes away. So there's the derivation of that. Okay. All right, let's use the transfer axis term on that page we just went over and go back and find the moment of inertia of a rectangle about its own base. But let's not do it with calculus this time. Let's just use the transfer axis term. So I'm back on page 660. So I bar x is what? bh cubed over 12. But I want to get the moment of inertia about the base. So this distance here is what? H over 2, I think. Okay. So I sub x is I bar x plus ad squared. I bar x is what? bh cubed over 12. Ad squared, the area is the base times the height. The distance is h over 2, and I square that. So I'm going to get bh cubed over 12 plus bh times h over 2 quantity squared. It's going to be bh cubed over 12 plus bh cubed over 4. I have to remember some of my fraction facts there and do a little factoring. Find the least common denominator. Bh cubed over 3 plus 3 bh cubed over 12. 4 bh cubed over 12, which is bh cubed over 3. Okay.
So not only b h over 2 and our a times base.
I'm sorry now?
And the step down, like you're calling our a
A?
times base.
Yeah, that's there, yeah.
You're calling our d h divided by 2.
Yeah, half of the height. All right, why don't we find the moment of inertia of this shape? And I don't know if I put that in there or not. This is just a 2 beam.
680.
680. Yeah, kind of is without the dimensions. Yeah. Let's use the transfer axis theorem. So on this one, I just happen to have the neutral axis on the bottom of that rectangle. So what do we got here? We've got I sub x is I bar sub x plus ad squared. Is that right? That's the formula I'd use. I bar sub x is what? bh cubed over 12. And I can get the a times the d squared. All right. Let's get some centroids on those things. Here's one. And there's one. So what I want is the distance from the neutral axis to the centroid. With that distance and that distance. So what do we got here? We've got half of 4 there, right? 2 inches? 4 over 2. The area is what? 12 by 4? 48 inches squared. And once you fill in the bottom there, we got just a couple minutes. Get the area and the distance for the bottom one. You get everything? No, because we're taking the moment of inertia about the neutral axis. So we're
Distance from the neutral axis,
yeah, because
the combined distance, like 2 plus.
no, it would be so we're told that we're going to take the moment of inertia about the neutral axis, which is what you usually do for a beam. So this is our new reference axis that doesn't go through the centroid of either piece. So to find the moment of inertia of each of those pieces about the neutral axis, we need the distance from it to the centroid of each of the pieces. We're going to have to do this in 2 steps, one for the top rectangle, one for the bottom.
Okay.
Yeah, so we're not combining them, we're kind of doing them one at a time, adding up the results. Okay. So we good with that? So 48 on the top for the area, 2 for the distance, 24 for the area on the bottom, 4 for the distance. And then we can just do the BH cubed over 12 for the top rectangle. I'm calling that A. Add in a term for the area times the distance squared. 48 times 2 squared. I get 64 plus 192. That's 256. And then I do the same thing for the bottom rectangle. Base of 3, height of 8. So 8 times 8 cubed over 12, plus the area, which is 24, times the offset distance of 4 squared. Add those together, I get 512. Add the 2 things together for A and B, and I get 768. Now that number tells you if this was a T-beam and it was loaded up, it'll get you some indication of how much stress it will have when it's loaded. And actually, I'm teaching strengths right now. We do that in strengths. We won't really do it in here. So the beam design stuff, we do a little bit more in strengths. So if that's a T-beam like that, and I load this thing up like that, and I've got supports under this thing, as you normally would with a beam, like that. That tells me when that beam bends a little bit, how much stress. That helps me to figure out how much stress is going to be present in that beam when it's loaded like that. That's the idea. All right. I'll get you a couple of these to do, 361 and 362. What we'll do, I'll cover these in class, and I'll have a key posted also. It'll be the 16th. We'll do a little, okay, so we'll do that for now. Let's do Monday the 16th, which is a week from today. And those are centroid. Those are the wrong problems. I'm sorry, I did. 341 and 342, those are centroid. We're trying to do centroid. So 341 and 2. Let's try that again. 341, 342. Okay, so 341 and 2 are going to be due Monday of next week.